So, welcome to lecture number 7 on this class stability of structure. So, let us briefly recapitulate what we were doing in previous class. So, we have just completed discussion on simplified system, system consisting of rigid bar and in which elasticity is imparted by concentrated, spring, translational spring and, rotational spring, and then we have classified the instability into several classes. We have demonstrated the equilibrium path. We have demonstrated that how the simple system equations are leading to a eigenvalue problem, through linearization that is providing us the critical load, and we have to explore the higher order derivative of potential energy. The first order derivative, of potential energy gives us the equilibrium. Now we are to ascertain the nature of equilibrium, whether it is stable, unstable or neutral. We have to explore on higher order derivative of potential energy function. Thereafter, we have also discussed about imperfection sensitivity, modal interactions of mode, right, with those simple examples. And then what we have started in the previous class, that we briefly touched on beam column. Okay. So we all are aware about the buckling of column that we have been taught in our undergraduate classes, right, on strength of material or mechanics of material, right. So here we are just trying to extend this thing. Okay. So you are discussing about the beam column, right, and we are trying to show a beam column is a structural system. Okay. So beam, it's a one-dimensional structural component which is loaded in the transverse direction, right. Okay, that is beam. And in case of column, column is a member which is loaded axially, axial compression. So beam column means it is both beam as well as column, right. So it is compressed, axially compressed like this. Okay, P, right. And then while there are many approaches to for deriving the different governing differential equation, but the approach that we are going to follow is the one based on energy. Once again, we have seen the beauty of energy approach, and precisely we have used energy approach until all the discussion for stability analysis. There are various formalism for stability analysis. Most convenient of that is the energy formulation. Okay, we are talking about potential energy. Okay, and then various derivative of it. Okay. So previous class, if you can recall that, we have derived the potential energy for a beam column, strain energy minus work done, and strain energy of bending, is nothing but EI by 2 integration 0 to L, d to W dx to square dx, right. And then in this beam column, what we have assumed that we have not considered the, we know the governing differential equation for beam, right, beam bending, right. So here in beam column, so this is the basically governing term which is describing the strain energy for bending, right. And then the work done by the axial load is nothing but P by 2 integration 0 to L dW dx square. So if you can recall, this term is nothing but this term is coming from the von Karman nonlinearity, which is a very essential term, for buckling. All over, even for linearized buckling analysis, we will see that we will make use of the von Karman nonlinear term. Okay, and that. So then from here we will see how. So here we will just use a simplified, little simplified, EI by 2 integration 0 to L. This I am going to derive W comma XX square dx. So comma XX means double derivative. Okay, here. So here this is just simplification of expression. Okay. Now the first derivative of this one. Okay. So delta pi need to be 0. Okay. First variation of the potential energy, so it's a function and potential energy function. First variation of the potential energy function to be 0. So if you do, then you just do that. So EI by 2. So differentiation is allowed under the integral sign. Leibniz rule is valid. Okay. So because W certain function has to satisfy that, and W is the function because it's elastic displacement continuous function differentiable, right? So integration 0 to L. So here 2 W comma xx, delta W comma xx dx. Okay. Now see we are differentiating, minus p by 2 integration 0 to L 2 W comma x delta W comma x dx. Fine. That must be equal to 0, right? So we will just simplify this further. So EI integration 0 to L W comma xx delta W comma xx dx minus p integration 0 to L W comma x delta W comma x x is equal to 0. Okay. So this is the equation we are getting by taking first derivative of the potential energy function, right? Okay. So I am removing that apart and then I will do further. Okay, I am removing this one. Okay. I will simplify this term. How we are simplifying? First, let me simplify, and then our aim is to convert delta W comma xx into delta x. Okay, so this we are following nothing but variational calculus. Little bit of in finite element you have learned little bit of variational calculus, right? Variational calculus. Okay. So what our aim from simplification, whatever we want to convert it through bypass integration W, all this we want to convert into delta W. Okay, this is our aim for simplification. Okay, so now what we will do, we are going to do, EI let this be outside. So first function, okay, first function integration of the second minus for integration derivative of the first integration of the second whole integration minus then here p once again first function integration of the second minus whole integration minus it will be plus derivative of the first integration of the second whole integration equal to 0. Now, the boundary term, whatever we are defining, we will take it. Okay, we will make it take it together. EI W comma xx delta W comma x, and this one I am bringing here minus p W comma x 0 to L. Okay. Now, what I will do? Look, here it is d delta W, right? But here it is still delta W comma x is there. So you have to first once again integrate it further. Okay. So we have now this term I will just so this one I am just once again integrating. So first function integration of the second minus whole integration plus derivative of the first integration of the second, this term, right, and then last term 0 to L p W comma xx W dx. So what simplification I am doing, you please try to follow that. Essentially I want to convert the derivative of differential of the derivative term into so now I will take it inside. So what I am going to do, EI W comma xx delta W comma x integration 0 to L, this and this thing, this and this minus, here I am going to do EI W comma X X X plus P W comma X delta W integration 0 to L, right. So, the boundary term I am basically combining, okay. Please know that delta Wx, please know delta W, okay, plus here what I am going to do, here integration 0 to, please note that here is d delta W. So, I will take it together EI W comma X X X X plus P W comma X X dx delta W is equal to 0. Clear? So, this is the boundary term and this is the integral term, right, equation, okay. Now, what I am going to do, all of you have noted down this one, please note it down. Now, you see, delta W is not is equal to 0, right, because delta W not is equal to 0. Well, I mean not necessarily, wait, one thing. Well, first let us see. I don't know, you see that integration 0 to L, this one dx delta W is equal to 0, okay. So, delta W is not is equal to 0, right, okay. And so, this, this one, now this, when I am making it integration 0 to L, okay, this particular integral 0 and L, of course, we are integrating over the domain, right, but this, these two limit can be arbitrary, okay. Okay. So, if delta W is not is equal to 0, if delta W is not is equal to 0, then this must be 0, you see, okay. This must be 0 if these two limits are arbitrary, okay. So, not all the cases you can write that, right, delta W, no. So, then this basically gives us a sort of governing equation, okay. So, EI from here what I can write that EI W comma X X X X plus P W comma X X is equal to 0, delta W not is equal to 0, because A and B it is integral, we are writing from 0 to L, between any A to B we can write, okay. So, this is nothing but the governing differential equation. So, this is nothing for dW dx4 plus P d2W dx2 is equal to 0. So, this is the equation for beam column. This was nothing but the beam, and when there was no column, no axial compression, this term was not there. So, because it is beam column, the beam is under axial compression, additional term is coming. Do you see that? So, this is the equation for the beam column. This is equation for the beam column, and delta, okay. This is equation for the beam column, okay. Now, so this gives us the governing equation, okay. Now, what about the boundary terms? Boundary terms will give us the boundary condition, okay. That I am going to show. That's the beauty of this, variational principle. So, from the energy function only started, okay, and this will give us not only the governing differential equation, this, but also gives us the boundary condition, okay. So, if you look at the boundary term, first this is the one boundary term. So, you see, so when we are when we are talking about EI W comma XX delta W comma X, when either they need to be evaluated at 0 or L, right? Any A and B, right? Any wherever the boundary is, right? Now, either this need to be 0 or this need to be 0 if it has to vanish, right? Right. So either either EI W comma XX need to be 0 or delta W comma X need to be 0, right? If the boundary need to vanish, right? Any one of the, so what if delta Wx comma 0 means what? Delta Wx means delta, what is this? This is nothing but dW dx. What does it mean? The slope is specified. What does it mean? This means the slope is specified. Slope is specified. It can be 0. So delta, so slope would, if the slope is constant, then the variation of variation of that would must be 0. Variation of a constant is 0, right? So slope is specified. That means theta is equal to dW dx is equal to theta sums theta sums theta, I mean theta 0. Understand? If slope is specified, then you don't, and what is this expression now? EI d2W dx2 is what? This is nothing but what? EI d2W dx2 is nothing but bending moment. So if bending moment is specified, then slope is unknown. If slope is specified, then bending moment is unknown. Do you see that complementarity, of the relationship, right? Either respective displacement is known. If you know the displacement, you don't know the force. At a support, if you know the support condition, then you know what is the what will be the displacement, right? You don't know the force. If you apply some force, you know the force, but you don't know the displacement, right? That's what essentially happens. So either slope is known or bending moment is known. If bending moment is known, that is the first boundary condition, right? So for example, when the slope is specified, you consider, what will happen if it is simply supported? Simply supported means what? Bending moment is 0. We know the bending moment. We don't know the slope, right? Now if it is free, at the free end we don't know the slope, but we know the bending moment will be what? 0, right? Okay, good. So we are done with the first boundary, right? Boundary term. What about second boundary term? Second boundary. So this is the first boundary term, right? First boundary term, boundary term. Now second boundary term is EI W comma X X X plus P W comma X. This must, so this multiplied by delta W 0 to L need to be 0, right? Okay. So that means either EI d3W dx3 plus P dW dx must be 0 or delta W is equal to 0. What does it mean? If delta W is 0 means deflection is specified. Deflection specified. If the deflection is specified, then you don't know shear force. If you know the shear force, then you don't know W is specific. For example, here what is it? W is 0. W is 0. If there is sinking support, W is specified. That del W is 0, right? Or if you at the free end, you don't know the deflection, but you know the shear force to be 0, right? So this expression is what? It is nothing but shear force. Shear force is EI d3W dx3 plus P dW dx. And if you can recall, this is nothing but dm dx plus P dW dx. So that means for a beam column, Bending moment, shear force is nothing but derivative of bending moment, but in additional term P dW dx is also coming. So, in the beam column there is a additional term due to shear force, additional term, the component of this, the P axial force is contributing in shear P dW dx. So, the shear force is different. So, you see that. So, what we have seen that you see the beauty of the energy function, we did not consider any physics, just from mathematics we have considered the energy functional, and from the energy functional by doing this little manipulation, and whatever we doing basically it is called that's what is called variational calculus. It gives through some simplification it gives not only the governing differential equation, but the boundary condition as well. So, if you want to solve this differential equation, you need to have this boundary condition. The otherwise also it is true, vice versa. That means, if you have a governing differential equation given and augmented by sets of boundary condition, you can derive a functional which by minimization of which will satisfy, by minimization of which you will get the solution of the problem. That is what essentially do in finite element. In finite element, what do you do? You are given a differential Galerkin method, Bubnov Galerkin, Petrov Galerkin. What you do? You are given an equation. Ultimately, see, when you start for the Strauss element, you start with the directly for the energy, right? But if you are given any differential equation for heat conduction, for fluid flow, and this and that, when you want to derive finite element, what do you do? From the equation and sets of boundary conditions, you try to derive some functional, and you minimize that function to get the solution, right? So, the way to get it is called variation. This is the subject of variational calculus, okay? Knowingly or unknowingly you know that little bit, okay? Of course, there are much more elements, these are nothing but very simple lessons, right? Okay. So, what we wanted to derive is the governing equation from the beam column. This is the governing equation and these are the boundary conditions, right? Either, okay? So, it is extension of the beam bending equation, right? But there is additional term. So, beam bending equation E I d4W dx4 was 0, but this additional term due to column this P is coming, and then in the shear force there is some change, otherwise rest of the things are same, okay? Okay, now we are going to discuss a very one characteristics of the beam column, that is we are considering a beam column here is subjected to P force P, okay, and we are assuming that, well, I mean there might be some forces etc. So, you have to it is maybe deflecting something like that, and assume that it is subjected to some load Q here, okay, and there is a mid span deflection and something is happening delta 0 whatever, okay, this deflection delta 0, okay. So, this is of length L, okay. So, now we can directly start with the governing equation, you can see find out, I mean you can directly start with the governing equation you can solve, but here I will do a little different, okay. So, here of course this is symmetric, right. So, if I consider deformed configuration, okay, the part of it, okay, and so here it is P, here it also be minus P, and if this Q, then there is a reaction force Q by 2, right, Q by 2, then here there will be some downward reaction force Q by 2, right, and I am assuming that this is maybe W and here from at a distance x, okay. This is the beam column deflector configuration, right. So, what is the bending moment here? Bending moment as a function of x, what is the bending moment here at this section, right? This section the bending moment will be nothing but see this P into W, right, P into W, and then these two P is forming a couple, clockwise couple, right, and these two also clockwise couple, right, this one. So, that Q by 2 plus Q by 2 into x, right, and this is nothing but minus EI d2W dx2, right. So, let us quickly solve it. So, now we are going, what we are going to do, d2W dx2, here it will come the plus P by EI into W is equal to minus qx by 2ei, right, and qx by 2ei means minus, I will write p by ei into x and then 2 then q okay. So, p by ei is nothing but we are going to define something lambda square is equal to p by ei, okay. So, defining p by ei as some function, right. So, then here we are what we are going to get d2w dx2 plus lambda square w is equal to minus lambda square q x by 2p, lambda square q x by 2p, right. So, now we are going to this is the difference. So, from the beginning moment we there is a governing differential equation E I d 4 W dx 4 plus p whatever, but why we are trying to follow this thing? One thing is that we want to solve that differential equation. It is a fourth order differential equation, and if the fourth order differential equation you want to solve, then you need to have what? Boundary condition, right, of the okay of, which allows until third order derivative there. So, you have to consider both the force and displacement boundary condition as well as force boundary condition, because you need to have four boundary conditions, right. We say evaluate the constant. I want to keep the difference order of differential equation low. So, that is what I directly work with the bending moment, because bending moment is E I d 2 W. You see that we have a second order equation, it is easier to solve, that is the reason, right, nothing else. We could have also solved using energy, that is also another way, huh? Okay, good. So, now what we are going to do? If this is the equation, let us solve it, huh? And keep that lambda square is equal to lambda square is p by ei. Ei is flexure rigidity, modulus of elasticity, I is the second moment area. Okay, so you see that d2w dx2 plus lambda square w is equal to minus lambda square qx by 2p. So, it is a non-homogeneous differential equation. So, wx will have two parts, one is w complementary function, one is w because of the particular integral or particular solution. Complementary function is nothing but the solution of the homogeneous equation. Homogeneous equation is d2w dx2 plus lambda square w is 0, right. So, if I give this d, the differential operator d square plus lambda square w is equal to 0. This is a differential equation operator, and d, the root will be d will be, you have 2 root plus minus I lambda. So, if you just substitute, you get the complementary function solution to be a cos lambda x plus b sin lambda x. That is the complementary function, right. A cos lambda x, b sin lambda x. You know why sin cosine, because if you exponential I lambda plus e to the power minus I lambda, by Euler's theorem cos theta is cos lambda theta lambda x cos e to the power I sin lambda x is nothing but cos lambda x plus I sin lambda x, right. So, then a and b are the constant, right. You know this thing. Now, we are going to do the particular integral. So, the particular solution will be nothing but, once again I am going to write that in a format d square plus lambda square, and here I am going to write minus lambda square q x by 2p, right. Here I want to this lambda square, I will take it out, 1 plus d square by lambda square lambda square qx by 2p writing this. So, I will just lambda square will go, and then 1 plus d square by lambda square inverse minus qx by 2p, and if you just do this binomial, d square lambda square plus d to the power 4 by lambda to the power 4 plus whatever minus operate it on d is the differential operate it on this. What we see that double derivative on x will be 0, right. So, had this only this thing particular integral is nothing but minus qx by 2p, right. So, I will total solution I am going to write a cosine of lambda x plus b sin lambda x minus qx upon 2p, right. That is the total solution wx, right. Now, we are going to enforce the boundary condition, okay. So, boundary conditions for this so at x is equal to 0, w is equal to 0, and then the second boundary condition what we are going to do, this is symmetric, right. So, at midpoint on the load at midpoint there the slope must be 0, right, because of symmetric boundary. So, x is equal to L by 2, you are going to do that dw by dx is going to be 0. These two boundary conditions required because 2 are known, right. So, when I am doing I am going to do x is equal to 0, w is equal to 0. So, w is equal to 0, x is equal to 0 means a, okay, plus b into 0 minus 0. So, basically a is nothing but 0, right. So, a is 0, okay. So, now wx simplified as b sin lambda x minus qx by 2p, right. Now, we are going to second derivatives which is dw dx is nothing but b lambda cosine of lambda x minus q upon 2p and 0 and b lambda cosine of lambda L upon 2 minus q by 2p. So, b is nothing but q by 2p divided by lambda cos lambda L upon 2. That means here it is q divided by 2p lambda cosine of lambda L by 2, okay, b. So, I am going to remove all other terms, right. You see, so wx become so what was p sin what wx become so it was a sin lambda x minus qx by 2p, right, and then a become if we just simplify a become q by 2p lambda, and here it is cosine of lambda L by 2 cosine lambda L sin lambda x minus q x upon 2p, right. That is the solution. What we are interested in, we want to find out the deflection under at midpoint, right. So, midpoint deflection if you want to find out, then that means that x is equal to L by 2, I am assuming that w is equal to delta 0, okay. So, here I am going to write, so delta is w x is equal to L by 2, and then if you substitute q by 2p lambda sin lambda L by 2, this here is cosine lambda L upon 2 minus q by 2p L by 2, and then here you will see that what we are going to get q by 2p lambda tangent of lambda L upon 2 minus q L by 4p, right. We will do little more simplification to get the mean one deflection. is that we will assume, see, we have assumed lambda square is equal to P by I, right? Here we are going to define another parameter u is equal to lambda L upon 2. That's what we assume, lambda L by 2. Then what we obtain delta is nothing but delta 0, okay, delta 0 midpoint deflect. What delta rather? Delta, you just put delta, okay, delta nothing but, so you see that, so q by 2p lambda, so well, you know, and then what we can do, q by 2p lambda, so q by 2p and so lambda L by 2 L by 2, okay, so E L by 4p and lambda u. So wait, let me see. Okay, let's write, okay, is 2p lambda tangent of lambda L by 2 is u minus let us write QL by 4p, okay. So then what we are going to do, so q by 2p lambda if you take outside, and then 10 tan u minus what will this be, q by 2p lambda, q we are taking out, p we are taking 2 lambda. So here it will be inside, you will see that here it will be lambda L by 2. Is it so? Is it coming correct? See that lambda will go 4p and QL, correct, right? Okay, so q by 2p lambda tangent of u minus u. U nothing but lambda L by 2, okay. We'll do little more simplification, okay. Simple, no. So now delta 0, that means deflection without P. What is the deflection? So what was the mid-passband deflection? So concentrated load of Q, QL cube by 48 EI, right? That was the deflection, na? Okay. So what we can do, delta by delta 0, that means delta by delta 0 is going to be, delta is what? Q by 2p lambda tangent of u minus u, delta 0 is q L cube by 48 EI, right? So this q will go, okay, and then here what is happening is that 48 EI on the top right, 2p lambda L cube 10 u minus u. Now this one, let us simplify though. So it is further. So this is nothing but, so basically 24, right? 24 EI by p lambda L cube, okay. So this one, this term is coming nothing, 24 EI by p lambda L cube. Here we will do one thing, 24 we will write, here we will write p by EI, okay, lambda L cube. So 24 p by lambda is lambda square, right? Lambda square lambda L cube. So 24 lambda L cube, okay, and lambda L 1 means 2u, 2u, u, so 24 by 8u, 3 by u cube, right. So, this term is nothing but 3 by u cube, 3 upon u cube, 10 u minus u, okay. We are doing some substitution just to simplify it, please note that, okay, nothing else. So, delta upon delta, so we will further simplify it, okay. So, you see that 3 upon 3 by u cube 10 u minus u, okay. Here we will 3 by u cube. So, what is the expansion from theta? U plus u cube upon 3 plus 2 by 15 u to the power 5, something like this, okay. 17 by 105 u. If you evaluate the factorial, then you will get this thing, dot dot whatever, and you see that minus u we are writing, and then just so this and this will go. So, what is essentially remaining? You see that u cube, this will go, so there will be 1, and then what will remain? 6 by 15 u square, okay, and then you will get, so 105, this is u to the power 7, okay, please note that. So, u to the power 4 and things like that, okay. Okay. So, all of you are following the derivation, right. So, we obtain delta by delta 0 is nothing but 3 by u cube 10 u minus u, and this one we are getting like this, okay. So, now what we will do? So, u square is nothing but lambda square L square upon 4, right, and lambda square is what? P by I, right, lambda square, this is L square by 4, okay. So, P, okay, P and this 4 I will take here. So, EI by L square, okay. So, here I am going to write pi square, and the top I am also going to write pi square. So, here I am going to write pi square P, and here I am going to 4 PCR. If it is simply supported, both end, then pi square EI by L square is nothing but critical load P critical. So, pi square B by 4 here, and pi square by 4 is nothing but, so what I am going to write this, please note that from here I am going to substitute it here, you see that, please. So, 1 plus 6 by 15 into u square nothing but pi square P by 4 P CR. Then I am going to write 51 by 105 u to the power 4 mean pi to the power 4 by 8 P by P CR square plus dot 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 whatever, and then you will see this will further be simplified to, so 3 by u cube 10 u minus u will further be simplified to, you see that, this 1 plus, see 6 by 15 pi square by 4. So, 6 into pi square 6 pi square by 60, okay. So, pi square by 10, and pi square is nothing but 9.8 something like by 10. So, it will be very close to 1, okay, and that is what I am going to write. So, it will be nothing but 1.1 plus 0.984 P by PCR plus 0.998 P by PCR square plus whatever, okay. What does it mean? So, may I write it like this? 1 plus E by PCR plus P by PCR square plus whatever. May I write it like this? 1 minus P by PCR inverse, say as a binomial series, right? May I write it like so. Ultimately, this become, so this from this, what we are getting, delta by delta 0 is nothing but 1 minus P by PCR inverse, or I can write delta is nothing but delta 0 divided by 1 minus P by PCR. So, this will give us an interesting thing. Why? Because, I am removing all other things, okay? So, what ultimately what I obtained is delta is nothing but delta 0 divided by 1 minus P by PCR. What does it mean? That means, if I don't, if the P is 0, if P is 0, then delta is nothing but delta 0. If P tends to PCR, delta tends to infinity, right? So, delta basically, so out of plane deflection increases, enhances with increasing P. What does it mean? The flexural stiffness reduces. So, axial force reduces the flexural stiffness, right? So, here you see that axial compression erodes the flexural stiffness. And during buckling, what happens? It's the flexural stiffness is so less then that a column will try to deform in flexure. See, any system, elastic system, any system try to attain the minimum energy configuration, right? Minimum configuration of energy, any system, right? Elastic system not an exception, right? So, you see that I am a column and somebody is compressing me, right? So, initially I will try to deform elastically, you see, but by axial compression, my U I will have epsilon x, del U del x, I am going to compress axial strain, but that strain energy will be stored inside me, right, and that will contain potential energy. But then as P is increasing, you will see, because it erodes the flexural stiffness, it will be easier, energetically favorable to deflect out of plane like this. That is what I am basically buckling, right. So, buckling essentially what happens energetically. So, beyond some threshold value of compression, axial compression, the out of plane deflection, the strain energy that is required, strain energy demand by out of plane deflection become lesser than the in plane, strain energy due to in plane deformation, and then the column tries to attain an energy which is energetically favorable by out of plane deflection, because axial force tend to erodes the axial stiffness, okay. This will be even more careful, you will understand it when we will do the finite matrix formulation or finite element formulation, but including geometric stiffness. But from here so here I am going to plot it. Here you see that if we plot delta versus Q, delta versus Q, then three scenarios you can see. So, you see that for three different, when P is 0, when P is equal to maybe 0.4 PCR, 40% of P, when P is maybe 0.7 PCR. So, that means here you see that relationship is linear. Delta 0 is nothing but what? What is delta 0? Delta 0 is nothing but QL cube by 48 EI, 48 EI. but then QL cube by 48 is being eroded. So here the axial, you see the slope of this line reduces, and the slope of this line is nothing but the flexural stiffness. So you see this inclination is reducing, and this is nothing but stiffness. So but the relationship between Q and delta remains linear. You see that? So this is for three distinct value of P axial force, and they are on different fraction of a critical load. So as critical load increases, as the axial force is higher and higher fraction of critical load, you see the flexural stiffness reduces. Okay. Now what is the relationship between P? Here I am going to write delta, and I am going to do P. Okay. You see that, and here P critical. Okay. So here you will see that at P0 there is some threshold deflection delta 0, and after that it will be asymptotically, right. So this is nothing but, this is 1 divided by 1 minus P by P here. Okay. So you say that if there is no axial force, then some deflection will happen. After that, as it is tending to PCR, the deflection will non-linearly increase, because this is a non-linear function. 1 by 1 minus P by PCR is a non-linear function. So the relationship between Q versus transverse force versus deflection is linear, but axial force versus transverse displacement is non-linear. This relationship is perfectly linear, so it allows the superposition to be valid. But when the relationship between transverse deflection and axial force is concerned, then it is non-linear. So there you cannot apply superposition for axial force. Okay, to find out the influence of the two axial force on the out of plane deflection. Okay, so you have to be careful there. Okay, you see that what I am trying to say? Clear? Now, what about bending moment? The bending moment. So this basically this factor. So what do we see? That on a application of axial force, amplify the deflection. So this factor we can define as amplification factor, and this amplification factor depends on P by P here, right? This some kind of displacement amplification factor. Amplification amplification factor is what? 1 divided by 1 minus P by PCR, right? So this amplification depends on P by PCR issue. Now same amplification what you have seen in dynamics. Dynamics also you will get amplification, but the mechanism is different. Okay, that dynamic amplification occur, it's a function of what? Frequency ratio. Frequency of loading, ratio of frequency of loading divided by natural frequency, and the damping also. But here it is static, there is no inertia force involved, right? So there is the displacement amplification factor for an axial load, right? Now for the bending moment, what is going to happen? Bending moment a maximum will be once again the midpoint, it will be nothing but P into L by 2, P into delta plus Q into L by Q by 2 into L by 2, right? So P delta plus Q L upon 4. So then we just substitute it there, and then this is Mmax, but then M0, if there is no P, it is nothing but QL by 4, right? So you will see the amplification for bending moment will be, that's why I am writing without I am just writing it that, So there will be amplification in the bending moment also. So this amplification will be so Max is P delta plus QL upon 4, and then if you substitute that, so here it will be QL by 4, and P and delta is nothing but QL cube by 48 EI delta 0 on 1 by 1 minus P by PCR, and then if you simplify it, will QL by 4 1 plus P L square by 12 bi 1 divided to 1 minus p by p here, and then you will see substitute this PL square by 12 vi. To simplify, it will be p by so everything we want to explain in terms of p by PCR. Okay, so ei by L square. So here is pi. So pi is pi square. Okay, so here you will see this. You will see 0.82 p by PCR. Okay, and then substituting. If you substitute this, you will see this a max is nothing but QL upon 4, and here it will be 1 minus p by PCR 1 minus 0.18 p by PCR. So what we have seen that you see that here is also this this is the bending moment without axial force, right? So mx or m, maybe if you want to put m, and this one you want to put m0. Okay, so amplification it's 1 minus because it is negative this it is slightly lesser, at least for this case, but it is not necessarily so. So there is amplification in the bending moment as well. So amplification in the out of plane deflection, amplification in the bending moment, both. Okay, and you see that amplification for the bending moment depends on, of course, this is predominant, dominant term 1 minus p by p here. On the denominator there is slight, because this the erosion of this term is a little 0.18, around 20%, right? Fine. So the same thing exercise you can also repeat for the for a beam which is axially distributed. Okay, so here you see that you take a beam here, okay, and it is axially force P, okay, and maybe it is uniformly distributed load of intensity dou q, small q, per unit length, and you can here also you can find out what is the amplification and things. You can you do not require essentially, you do not require always to use the whatever approach you are using, but you can also use energy approach. Energy approach is a little significant. You try to do this exercise yourself. I am just giving you the hint how you will do that. Okay, so you see that when you write the potential energy function, phi is Ei upon 2 integration 0 to L d2w dx2 dx minus p upon 2 integration 0 to L dw dx square dx, and then because there is a transverse load q, here also you integration, here it will be q, I am assuming qx and wx dx, right? And then so, and you can use Rayleigh-Ridge method. Okay, Rayleigh, you know what is Rayleigh-Ridge, right? You have done Rayleigh-Ridge in dynamics. Find out natural frequency, right? Rayleigh-Ridge, you can assume W is equal to W0 sine pi x pi L, assuming that it is simply supported. Simply supported means this basically satisfied the essential, the force boundary conditions. So, essential boundary condition, that means here W is equal to 0, here W is equal to 0, sine x is equal to 0 and x is equal to L sine pi, right? So, then you basically substitute in this expression, right? Then if you substitute in this expression and then integrate it and simplify it, and you will get it. Okay, so I am just writing down the intermediate steps, but you can follow yourself. Okay, so here if you do, then pi, you will get that pi will be, if you substitute it here, then pi will be Ei upon 4, here I am assuming this is maybe delta, okay, delta of pi to the power 4 delta square by L cube minus 2 q0. Q is basically q0 here, q0 delta L by pi minus P pi square delta square by 4L. Please note the integral, okay. These integrals are standard integral, right, integration 0 to L sine square. You have to use this integral pi x upon dx is equal to L, okay. This integral you please recall, okay. Integration 0 to L cosine of square pi x L dx is equal to L by 2, and integration all this identity you have to use sine pi x by L, okay. L, these are all a small l, L is nothing but pi upon 2L. So, all these things you use, and then what we get, you will see that. So, this is the potential energy function, and then you simplify del pi by del pi d pi by del delta must be equal to 0, and del pi by del delta is equal to 0 when you do, you will get that delta is nothing but 4 q 0 L to the power 4 divided by pi 1 by pi pi to the power 4 p pi square, okay, fine. And if you want to put substitute delta 0 is nothing but 5 q L to the, what is the deflection for some, if it is a uniformly distributed load, 5 q 0 L to the power 4 by 384 EI, right, isn't it? So then you will see that delta by delta 0, if you substitute, and if substitute you will see, once again you will see that here 5 q 0 L to the power 4 by 384 EI 1, and then 1536 by 5 pi to the power 4 1 by 1 minus p by PCR, and this is nothing but it will be, this term is nothing but it will be 1, okay. So, here see delta by delta 0 is nothing but well, this is delta actually, okay, and this is delta. Delta 0 is nothing but this is nothing but 1 by 1 minus p by PCR. So, do you see how the same thing is coming, delta is equal to delta 0 1 minus p by PCR. Even for this also the same relationship is we are getting. So, the amplification factor is nothing but 1 by 1 for the uniformly distributed. However, the expression for the bending moment amplification will be little different. Bending moment expression I am just writing, this will be a max is nothing but like without P, the maximum bending on WL square by 8. Here it will be, this expression will be little different. You work out yourself, but I am just writing P by PCR 1 minus P by PCR and plus 1.03 P upon PCR. So, what do you see, that amplification factor for this uniformly distributed load is same, but in the bending moment amplification will be little different. Here see earlier it was 1 minus 0.18 something, but here it is 1 minus P by PCR plus 1.03. So, here amplification is little higher than the previous one, right, because earlier in the denominator, in the numerator it was 1 minus 0.7. But here resultant term, if you see, there is 3% increase in the denominator, in numerator. Denominator remains the same, okay. So, there is the, as far as bending moment amplification is concerned, for this case slightly higher than the previous case, okay. So, taken together you can, what we conclude that the presence of axial force in beam column basically it enhances the deflection, there is some deflection amplification of displacement which depends on P by PCR ratio, and also subsequently there is amplification in the bending moment as well, okay. But bending moment amplification varies case to case, okay, and we have demonstrated both the differential equation approach as well as energy approach. Clear now? before completion of today's lecture, we are going to demonstrate one very important stuff, that is the effect of shear deformation on backling load. This is extremely important because there was failure occurred by neglecting the shear deformation. Okay, there was a big there was a large truss which fails because the effect of shear was not accounted in design. At the time our knowledge base was not sufficient, it was not enough, it was not extended, and the effect of shear deformation on buckling load was not known, then that leads to failure, and that was significant amount of casualties and lives. Okay, so that's what we are going to demonstrate. So here what we will do, we will consider a case, we can consider a simple so one second, simply supported thing. Okay, PP. Okay, so what do we know this shear force? Shear force is nothing but EI d3W dx3 plus E dW dx, and this is nothing but the expression that is coming from bending moment, and the other component is coming from the axial force, right? This is the total, right? The contribution from axial force, contribution of bending moment. Now, you see the strain energy of bending. So, strain energy will be two strain energy, one is bending and one is shear. So, the component of axial force that contribute to the shear is nothing but P dW dx, right? Okay, and that we can also you see, we can also see, so it, I mean, if you consider, you see axial here like P, okay, and then it is deforming, it's deforming here. So you just consider this P and you consider a small thing here, here. So here it is P, here it is P. Okay. Now you see that this angle theta, this angle theta, this angle theta, this angle theta is what? Theta is dW dx. If we consider deflection, transverse deflection defined in terms of Wx, and I am considering x to be aligned along the axis of the column, right? So now you see that some of these, this one component of this will will act here, and then in this will act here. This I am considering this shear, okay, shear, okay. So this component, because of P, what is this component? This is this angle is what? Theta. So P cos theta, and this is nothing but P sin theta, right? So P sin theta, and P sin theta means P theta, and P theta means dW dx. So you understand the origin of this term P dW. It's very simplified, it's a very ad hoc way, quark way to show, but that is, I thought that I will just show it to you. So otherwise you will say that from what the hell physically you are getting this term. You see that what I am getting, why? Yeah? Of course the moment contribution is there because of this. Okay. So now if I want to write down the bending energy, I want to use Rayleigh-Ritchie method, Anchi method, right? So you understand the origin of P dW dx term. See what we have obtained P dW dx previously from variational approach, right? But it is physically also meaningful. You understand from here, right? Because of P. Of course, there is additional term that is coming because of the bending, right? That is dm dx, which is nothing but EI dt. Okay. So now bending energy, if I want to write, of course, what I have written that EI by 2 integration 0 to L, bending energy is d2W dx2 square dx. That was the bending energy, right? EI by 2. This one plus. If I now want to put the shear, contribution of shear, then may I say that what is shear? See, all of you have done strain energy chapter, right, in your undergraduate, right? what is the strain energy for shear? V is the shear force. I am assuming V. And what is the respective shear deformation? V by AG. AG is the shear stiffness, A is the area, and G is the shear modulus. But there is a shear correction factor, right? What is the shear correction factor? N, right? Shear correction factor is a factor which takes into account, because see, traditionally in beam bending theory, you do not care about the shear deformation. But the first order shear deformation, the theory proposed by what? Timoshenko's shear deformation theory, first order shear deformation. In beam it is Timoshenko, in plate it is Reisner and Mildin, right? And in cell it is by Nagdi and others, right? So, here their first order shear deformation, assuming that shear deformation is nothing but one additional rotation of this the deformed section of the beam section, right? But shear stress distribution is never uniform, right? It is always parabolic. So, there is some incompatibility. In order to take that, in order to have the consistency, you need to have another factor. Okay. So, that factor is nothing but shear deformation, shear correction factor. And what is that factor? This factor depends, of course, properties of the section and material, etc. But if you take it 5 by 6, it can vary from 2 by 3 to 1, but 5 by 6 typically you say na. Take, so it is N V square by 2 AG into dx. That is the way N is the shear correction factor, N is the shear correction factor, and V is the shear force, and AG is the shear stiffness, right? So, now you see this expression we are going to simplify a little bit. So, from there I am going to write it here, So, total strain energy, what? Total strain energy I will still write bending plus shear, but what I will do, I will not use this term directly. I will rather use, I am considering a simply supported beam column, and then I will, what is the other way to write the bending energy in terms of bending moment? Please recall other m square dx by 2 EI, na? That was the expression for the bending moment. This is another way to write. This is in terms of displacement, but this is in terms of bending moment, plus integration 0 to L. I am writing N to AG dx, and N by 2 AG, and V I am going to, this V is nothing but P dW dx, okay? P dW dx square dx. Now, you may wonder why I am not substituting dm dx. Please note that dm dx has been taken here, the bending energy. So, I am only just considering the term P dW dx, okay? So, this way here, okay? Now here what is the bending moment here? Here the bending moment M, x is nothing but P into W. Here, because if it is a out of plane deflection, out of plane deflection W, right? W is, so for in Wx, so at any section, P into W, right? That is the bending moment. So, I am going to write Pw, and this rest of this is in terms of W and P. I will do this thing in the next class, okay? Thank you for today's class lecture.